All right, so welcome to MathStat 341 probability. This is lecture 5. And what we're going to be doing today is talking a little bit about some things we've already discussed. We're going to go do those a little bit quickly, the factorial function, binomial coefficients, and then we'll start actually using probability to calculate things that you may want to use in practice. So calculating probabilities of poker hands. There are, I guess, places you can go where you can apply your knowledge of calculations of probabilities of poker hands. I will leave that as discussions for outside of the class. First, this is just a theoretical interest, trying to calculate what is the likelihood of getting certain combinations. The payout rates, not surprisingly, should be related to these probabilities. There are many times in games when the payouts and the probabilities are not properly aligned, and you have the opportunity to take advantage of that. I want to try to put in some pure mathematics as well. I will talk a little bit about Pascal's Triangle for a couple of reasons. One, it's absolutely beautiful. Two is there are probably some things about Pascal's Triangle which you could have been told about years ago but never were. And so I want to just put that on your radar. And the third is a theme of this class is it's not enough to be able to compute something. We often want to be able to compute it in a reasonable manner. And so I want to talk about what is necessary to do calculations efficiently and quickly. And I'll give you, some examples of stuff like that. So efficient coding is going to be extremely valuable. How many of you are comfortable coding basic things, for statements, while loops, stuff like that? All right, so it looks like almost everybody is. If you're not comfortable, send me an email. I think there's no written homework due this week to just make sure that everybody gets to the point where you can code well. If you can code well, you can almost always code better. And a lot of it is trying to figure out what is the best way to do something, or what is a good enough way to do it with the resources you have. Anybody know roughly how much RAM your computer has?
8, I think, minus 8.
Yours is 8?
Yeah.
8 what?
Gigabytes.
Gigabytes. I remember getting an expansion to get up to 16 kilobytes when I was young. Kilobytes. Okay, so when you have a system with very limited resources, boy, do you have to be efficient. The other thing is when you're writing code, what is the purpose of the code? Is it to solve a specific problem, or is it to have something available that can then be easily modified for a bunch of other problems? So when we do some poker hands later today, I could write a general program that can calculate poker probabilities. Or if there's a very specific probability that I want, I could actually adjust my code to take into account some of the special features of that problem. And so we'll talk a little bit about that in a bit. Okay, so the first is Pascal's Triangle. Everybody should have seen this before. So you have ones going into two diagonals, and then each number is the sum of the number above to the left plus above to the right. And so we talked earlier about Pascal's triangle, and we talked about the relationship, n plus 1 choose k plus 1, whereas n choose k plus n choose k plus 1. And we proved that by story. You could also prove it by just brute force algebra. We know what n choose k is, just multiply everything out and see that it's true. A lot of proofs are like that, and they're extremely unilluminating. That you then have to do something related, it's just another brute force calculation. You don't have a deep sense of why it's true. The telling the story, we had n wonderful students from Williams and one student from an also ran, as US News Report calls them. We would actually put in over here two coefficients, and the coefficients would be n choose 1 and n choose 0. But because each of these equals 1, there's no real reason to keep them. A big result is the binomial theorem, and we will use this when we calculate probabilities all the time. X plus y is the following sum. So it's the sum of n choose k, x to the n minus k, y to the k, or as most of us prefer, x to the k, y to the n minus k. By symmetry, it doesn't really matter. The simplest proof that it doesn't really matter is addition is commutative. So this is the same as y plus x. That's the easiest way to prove that these two expressions have to be the same. You can then use that to immediately deduce that n choose k is the same as n choose n minus k. And again, this was the star belly sneeches. If you choose k out of n to have a star, it's the same as choosing n minus k not to have a star. The binomial theorem is extremely important, not just for probability, but you've also used it in calculus. So in calculus, if we had f of x equals x to the n, f of x plus h was x to the n plus n h x to the n minus 1 plus h squared and higher. And so when you were trying to calculate the derivative of x to the n, we use the binomial theorem. We actually don't need the full proof of the binomial theorem. All we need to know is it starts off x to the n plus n h x to the n plus, sorry, that should be n minus 1. And then every other term is going to just involve h squared and higher. That is sufficient to prove the formula for the derivative of x to the n. If you want to calculate the derivative of x to the 3/2, you can't just argue like this. And this is one of the things that's often confused in calculus. And if there's time at the end of the day, I might talk a little bit about that. The binomial theorem, as written over here, needs n to be an integer. So whenever you're using results, always check and make sure that whatever conditions you need to be satisfied are. And so this is assuming n is an integer. So there's a lot of ways to prove it. So if n equals 0, we're willing to accept that anything to the 0th is 1. But for n a negative integer, we do not have it as well. Correct. N has to be a positive integer. There is a generalization of the binomial theorem that holds for any n. So n could even be an irrational number, but then you'll have an infinite series. All right, so the proof. One is by induction. And what we can do is we can write x plus y to the n plus 1 as x plus y to the n times x plus y. So that would then be x plus y to the n times x plus x plus y to the n times y. Raise your hand, please, if you have not seen proofs by induction. It is not a prerequisite for this course. So if you have not seen proofs by induction, let me know. This is where you assume it's true for the base case, and then show that if it's true for n, it has to be true for n plus 1. Now it's true for everything. And so when we look at x plus y to the n, we can then figure out what's the coefficient of, say, the x to the k plus 1 term. So, look for the coefficient of x to the k plus 1, y to the n minus k minus 1. And so for the x plus y to the n times x, well, if I want to get an x to the k plus 1, I need the x to the k y term here, y to the n minus k. And then actually this should be n plus 1, sorry. Because we're doing x plus y to the n plus 1, so it would be, so let's just do it as x to the k. We'll make it a little bit easier. So we want x to the k, y to the n plus 1 minus k. So we would need the x to the k minus 1, y to the n plus 1 minus k term here. And then over here, since we're multiplying by a y, we would need the x to the k, y to the n minus k. And so when we put things in here, what is the coefficient? Well, by induction, we would get, it's going to be n plus 1, choose, let's see. Oh, no, it's not, it's k minus 1 plus n plus 1 minus k. What does that sum to? It doesn't sum to n, plus 1, it sums to n, right? So it's going to be n, choose k minus 1, x to the k minus 1 times x would get us all the way up to x to the k, y to the n plus 1 minus k. And then this piece, I need the x to the k term. So it's going to be n choose k. And that would become x to the k, y to the n plus 1 minus k. And you can now see here are our two coefficients. So this is one way to do it by induction. Here's another way. So let's say we have x plus y to the n. So that's x plus y times x plus y all the way down to x plus y. I claim the terms of the form x to the k, y to the n minus k, 0 less than equal to k less than equal to n, and that's an integer. And the reason is for each term, I choose either an x or a y. I have to choose n terms, so the sum of the power of x plus the sum of the power of y has to equal n. And now if you look at it, if I want to get x to the k, y to the n minus k, I have to choose k terms to give me an x. How many ways can I choose k terms from n to give me an x? So n choose k, give an x. Okay, so now how many factors are left? If we've chosen k factors from n to give us an x, how many factors remain? N minus k. And if we have n minus k, of those n minus k, how many of them have to be what? All of them. So it's n minus k. But what's n minus k choose n minus k? It's just one. So when we write that the coefficient is n choose k, really you could write it as n choose k times n minus k choose n minus k in an excessive burst of notation, right? But there's really no need to do this because this is just one. So since it's just one, why bother writing it? One reason to write it is generalizations. So when we get to multinomials, then this will be useful. But what we're doing right now is not really that necessary. Okay. Any questions about this? So this is the binomial theorem. Last one is a great application. Is when x equals p and y equals 1 minus p, 0 less than equal to p less than equal to 1. That's one of our most useful applications, because then we can talk about trying to calculate the probability of something happening as p, it doesn't happen as 1 minus p. If we do it n independent times, what's the probability we have exactly k successes? So this will lead to the binomial mean of variables. And this is one of the reasons why this is such an important result. Okay. So how many of you have ever looked at Pascal's triangle where you replace all the odd numbers with a dot and all the even numbers by just deleting them? All right, so let me see if I can. This is the short version. No, okay, so I've got to just. So unfortunately, I have to switch the share to. So what I'm going to do is this is the original version of the code that I wrote. And rather than having Pascal's triangle start at the top and fall down, it was easier initially to code it starting at the right and going at the left and going to the right. Makes no difference. If it really bothers you, just take a little bit of nap and put your head on you and just rotate yourself 90 degrees. Now, as you add more and more rows of Pascal's triangle, of course, it's going to take more and more space. So what I'm going to do is I'm going to renormalize so that at every moment in time, I am squishing it so that whatever I display is always going from 0 to 1. And so just however many rows I have, I just squish it so that it stops here. And that way I can keep displaying it. And you can see what happens as you add more and more rows. And again, if it's an odd number, it's a dot. If it's an even number, it's empty. So if I hit play, you can, this code in Mathematica where it's going to start generating. And it's just, you can have lots of different things in terms of the speed at which you generate and the number of rows in which you generate. So now it's starting to generate, it looks almost like an Imperial Star Destroyer at first, and the start of Star Wars. And you can see this incredible similarity of structure. It's interesting, it seems to have some trouble displaying it on the screen. It's doing a little bit better on my computer. But I put links there that you can click on it. And the question becomes, how do you compute something like this? Now, if you are really good in computer science, you can make an extremely recursive algorithm that keeps pulling various stuff. If not, you have to worry about how much storage space do I need? If I need to calculate one level, do I have to have all the previous levels saved? Well, I actually only need the previous level. And I only need the previous levels. I only need if it's a 0 or a 1. But if I do that, if I want to calculate the millionth level, I need to know the level before that. And so do I have to calculate everything, or like the Fibonacci numbers, can I jump ahead? And there are ways that you can jump ahead. If I start trying to do the calculations, if I do n factorial over k factorial n minus k factorial, if n is of size 10 to the 200, I can't do those factorials at first. So I need clever ways to group the multiplications. Well, I don't want to leave the integers, because if I leave the integers, I start getting rounding errors. So there are things you can do. So I'm going to just leave this as an exercise for you to think about if you're interested. How would you code this efficiently? And again, if you know the previous row, you only need to know the previous row, even or odd, to figure out what the next row is going to be. But if you want to just compute one row, how do you deal with the huge, huge numbers that can arise? Okay, so going back to the lecture. So what I want to shift to now is poker. It makes it a little bit large. Okay. So if you've never played poker before, absolutely fine. Is there anybody who has not seen a standard deck of 52 cards? Somebody want to describe a deck of 52 cards? What do you have? There are two colors. There's reds and blacks. Each color has two suits. The blacks are spades and clubs. Reds are diamonds and hearts. Good. So those are the possible cards. In a lot of games of poker, you are dealt 5 cards. In other versions, you have different number of cards that you are dealt. Sometimes you have cards that you share with someone else. Sometimes there are wild cards. We will just do the standard simple case of you are dealt 5 cards. And here, in rank order, are the different possibilities. So the highest possibility is a royal flush, then a straight flush, then 4 of a kind. And if 2 different people have a full house, whichever one has the highest of their 3 wins. Do you have to worry about 2 people having the highest 3? Why not? There are only 4. So you and I can't both have 3 10s unless, I'm sorry? What do you mean? Oh, unless you, right. So if we each dealt 5 cards, the only way that 2 of us can have 3 10s with no common cards is, nope, no, well, okay, no wild cards. Not a fair deck, or someone is cheating. Anybody ever see the movie The Sting? So one of my favorite scenes in The Sting is they know somebody cheats a card, and he arranges it. So he's dealt 4 9s, and the person he wants to bankrupt is dealt 4 3s. So the person's going to stay in for quite a while. And they know that this is coming. And so he is carefully opening his hand, and he sees 3 3 3. And he knows he's going to be picking the 3 very soon to get up to 4 3s. But he's prepared for this. And so the bidding becomes very high. He goes 4 9s. 4 jacks. And of course, the mob guy is furious, and he yells at his aide who was supposed to fix the deck. And the guy goes, I don't know what happened. I know I dealt him 4 3s. Well, what was I supposed to do? Accuse him of cheating better than I was? You can't have 4 jacks. I know, because I dealt you 4 3s. So the pigeonhole principle is very valuable for something like this. But what if you get to something like 2 pair? is it possible that we could each have the same two pair? I think if that's the case, you then look at the fifth card. And then if the fifth cards are the same, and then you might look at, if the fifth card is, a spade that beats a heart, that beats a diamond, that beats a club. That might be the deciding factor. Is it just a split? Yeah, I mean, you can do it several different ways. If you want to have a definiteness that there has to be a unique winner, you can then impose that we'll put in suit over there. And so you just have to worry about some of these things. So we want to calculate what are the probabilities of certain hands happening. And when you do probability, you always want to make sure you answer the correct question. So one question I could ask is, if I'm dealt 5 cards, what is the probability I have 2 queens? What would my hand have to look like if I have 2 queens? So what could my hand look like? So, again, these are calculating the probabilities. I just pulled them from Wikipedia. So let's say I want to calculate, 5 cards, hand has 2 queens. How would you compute that? What could my hand look like?
You have 2 queens.
Okay, 2 queens.
You have 3 cards that aren't queens.
So this is where it gets tricky. I have 2 cards that are queens. And then for the remaining 3 cards, they could be a queen or not. Right. So it's exactly versus at least. So when you hear a hand has 2 queens, how many of you think the hand has exactly 2 queens? How many of you think the hand has at least 2 queens? I would interpret it as it has at least 2 queens. It is not well written. This is very poor. Now you can be misleading. My father did this years ago to my wife, and she was to his wife, and she was not happy about this. They were at some party, and he was chatting with one of her friends, and then my mother was somewhere else, and my mother eventually ran into that person, and the person said, I didn't know you were married to somebody before you were married to Bill. What? He said your son from your first marriage is now in college. Is that an accurate statement? Yes. Is it a misleading statement? Absolutely. Right? When you say, yeah, you're the son from her first marriage, it seems to imply it's not you. However, it is easy to be misleading. So over here, it is much better to be very explicit. So be explicit. Let's do exactly 2 cards, exactly 2 queens. So we want to count the number of hands that work and divide by the number of hands. So how many ways can we form a hand with 52 cards? So from 52 cards that has 5 cards. So we have 52 cards in the deck. We want a hand with 5. 52 choose 5. And we are doing order doesn't matter. How many of these hands have exactly 2 queens? That's the question. So how many possible queens are there? 4. How many of those queens must we take? So there's the 4 choose 2. Now, how many cards are left in the deck? After we choose the 2 queens, how many cards are left in the deck? Be very careful. Yes, it's 50. There are 50 cards left in the deck. Of those 50 cards, how many am I willing to draw from now for the rest of my hand? 48, because I can't draw any more queens. I want to have exactly 2. So it'd be 48. And how many do I have to draw? 3. And then note, 4 plus 48 equals 52. 2 plus 3 equals 5. This is a good check. Well, not a check. This is a good check. Okay. So any questions on how we would calculate exactly 2 queens? All right, what if we want at least 2 queens? Cultural extra credit. Can anybody name me 2 members of the band Queen? Okay.
Dusty Simmons.
I mean,
Well,
well,
we got Brian.
all right, so email me for cultural extra credit. All right. Should play like We Will Walk You to wake everybody up this morning who were coming in. All right. So how can we calculate the probability that we have at least 2? Bottom term is the same. So what's the top going to be? Okay, so we have the 4 choose 2. So is this the answer? 4 choose 2, and then we have 50 cards left and we choose 3. And we divide by 52 choose 5. So is there a problem with this?
It doesn't make sense. Or it's like, if you
Right. So if I have, say, the queen of spades and the queen of hearts and the queen of diamonds over here, well, do I also count that with the queen of spades, queen of diamonds, and the queen of hearts over here? We have to be very careful about double counting. So what we can do is we can calculate something like this. What I've got over here is, I'll just calculate the probabilities on my computer, and I'll just display them. So the question is, are we overcounting or are we undercounting? Yes, it does. It's a great warning. You know, when they do not sum to 52, it seems like I am counting things too many times. So if I do this, I get 10 over 221, which is approximately 4.5%. How else could we calculate this? I could have exactly 2 queens, and then I have 48 cards remaining, and I have to choose 3. Or what could I have? So what I want to do is I want to break things into mutually exclusive cases, so I don't double count probabilities. And if they're mutually exclusive and they're exhaustive, they sum to every possibility.
So could you do 4 choose 3?
Yep. And then what would it be? 48 choose 2. And last would be 4 choose 4. 48 choose 1. Divided by 52 choose 5. And so now, this is just, you know, some really concise code to compute. And so we see the answer is equal to that, which is approximately equal to 4.16%, about 4.2%. So we can see it overcounted by a little bit. Not a tremendous amount, but it did overcount. And you can see the advantage of being able to write some simple code. Rather than calculating each one, I said, look, I've got a sum of 4 choose k, 48 choose 5 minus k. It goes from 2 to 4. There's one other way to calculate this. So it's 1 minus what? Right, so I could have no queens, 4 choose 0, 48 choose 5, plus 4 choose 1, 48 choose 4, over 52 choose 5. And so if we do that, minus, so K is now going to go from 0 to 1. And again, I did this just for the sake of, academic honesty and whatnot. Do I really need to do this calculation? Why not? Because I know what the answer is, right? It's the same as before. Exactly. And so in fact, if you use the binomial theorem, you can prove that they have to be the same. So really, the second and the third method are not independent tests. They're really the same by the binomial theorem. So we are now in the unfortunate situation where we have two methods, and one method gives one answer and one method gives another answer. How do we know which one is right? Anybody ever? Yeah. Play some poker. How much poker do you want to play? How much is a lot? Give me some rough idea. 1 million. That's what we want to do. That's the kind of dedication you need to get an A in this course. I'm willing to commit to playing 1 million hands of poker if that's what it takes to figure out what the answer. I'm sorry?
Somebody else's money.
Oh, absolutely. We have faculty entertainment funds. You need to phrase it very delicately. And I assume that this has to be played in a real casino, because if it's not played in a real casino, that could affect the probabilities. Yeah. Okay, so field trip. Exactly. Oh, absolutely. Absolutely. All right, so we could write a computer program to play 1 million hands or 1 billion hands, and then just see which do we think is going to be right, because 4.5 and 4.2, while they're close, they are pretty well separated. And so we can then try to figure out which one it would be. All right, so let's try to talk about writing a computer program to do something like this. I'm going to stop the share, and I'm going to move to the code. Okay, so is this large enough that people can see it without too much trouble? Okay, so the stuff I did over here, I don't really need. This was just calculating the binomial probability, so I'm going to just delete that. So what we want to do is we want to write a computer program to investigate the probability that we get 2 queens and 5. So 2 queens and 5, and num will be the number of simulations we do. And so I'm going to just do the code in Mathematica. You can use any language you want. Your good coding skills is you always close off a section as soon as you start. So if you have a begin, you close it off immediately with an end. And you put in comments what things are. So num is the number of hands, 5 cards, and then success is 0. How often we have 2 and 5 cards. That's the first thing we need to do now. To write this program. So DL5 criterion. To DL5 criterion, what do we need? We need a depth. So how do you want to define your depth? So we could have a tuple of your 52. And what numbers do you want to have in your depth? I'm sorry?
I guess we could have this.
So think about how you want to do it. You could have the numbers 1 to 52 and say maybe the queens, if you're doing a general deck, maybe the ace is 1, 2, 3, 4. The kings will be 49, 50, 51, 50. So that's one way. So you could do it as pairs. You could do it as pairs, or there's a better way. So my deck, I'm going to initialize exactly as queens and not queens. I'm going to put in 4 cards as the queens, right? And then for equals 1, n less than equal to 48, n plus dec equals append to dec 0. So dec of and 48 non-crease. Now, what's nice is this is going to be ideally suited for the problem we're studying, right? I don't care about anything else. Now, if all of a sudden after this I want to tweak, then it's not going to be as good. All right, so now what I want to do is I want to do the main part of the program. So for n equals 1, n less than equal to the number, n plus plus, now I have to choose 5 cards. How do I choose 5 cards? So we can often test things. So test 1, 2, 3, 4, 5, 6, 7. Random sample. And so that will pull 5 elements at random from test. So if you're ever not sure about what, so if I just do question mark and then the name of the command, it pops up some information about it. And then if I click on this, I can get more. I have local documentation. So I want to see a bunch of other documentation. And so here it starts to give you information about the function random sample. It gives a pseudo random sample of n of the EI. So it just pulls them. And you can see that this does what you want it to do. And so out of curiosity, how many of you actually have reference books for computer languages? So when I was young, that's what you had to do. Because the computer programs, there was so little space and so little memory. Now, it's not only on the web, you have local lookups, which we did not have when I was young. It's very easy if you forget something. I strongly urge you to have a second window open when you're programming. And if you're not sure about something, just practice it there. Put in a lot of print statements. I often have an extra command in my programs called print. And I'll do some if statements. If print equals 1, print this out. If print equals 2, or if print is less than equal to 2, print this out. And then that way, when you're running things, you can set it up so that it will give you some output consistently if you want it. But then if you don't want it, you just change the value of the print and it won't display anything. So now over here, so I have and, which is my set. It's going to be random deck and 5 cards. So how do I tell if I have at least 2 queens? Good. And that's the value of using numbers rather than letters. If the sum of the hand is at least 2, have at least 2 queens. So and sum is equal to the sum and this ith element. I goes from 1 to 5. I'm hard coding it because I know exactly how many things there are. And so now, if and sum is greater than or equal to 2, then now print is we'll do 1 point, we'll do by 100. This just sort of prints it up nicely. All right, so now if we do 1 million. That was what I believe was suggested. We should play 1 million hands. And so we'll see how long it takes to do a million. Now, that wasn't too bad. 4.14. And the actual answer we had from earlier, 4.16, I think it was. So that's not that bad. What we could even do, we could add is 100, 0, and then I shouldn't have deleted all that stuff. The sum of binomial, what choose k, binomial 48, choose 5 minus k, no, because I was, oh, and I forgot to write what k goes from. This would be k goes from 2 to 4. I'll just make it a little bit smaller, just 2. Okay. And so you're doing 100,000, took less than a second, 4.14. Basically, every time we go up a factor of 100, we should gain an extra decimal. And we'll prove that later. So this took about 5 seconds. We got 4.18. The correct answer is 4.16. That's not too bad. And we could do other stuff. We could put in some print commands to just really give us a sense of how long things are taking. So for instance, again, I'm just trying to show you some coding techniques right now. So I'm going to print here under the following. If mod n divided by 10 and we'll only do this one. What's the advantage of this? So if I have a very long program and I have no idea where we are, I might just abort it in frustration when we're almost done. So I want to have some sense of how long it's taking. You can have it print out where you are at that point. You could print out what is your success rate to date at this point, so that if the program crashes, you don't lose everything. So right now, what I'm doing is, how many of you are familiar with clock arithmetic? If it's 10 o'clock now, what time is it in 5 hours? 3. So 10 plus 5 equals 3. Well, it does on a clock, because every time you go around by 12, you reset. So what modular arithmetic does is, I just care about is n a multiple of the number here. So I'm taking the number of iterations I'm doing and dividing by 10. So every time that's 0, I've done another 10%. So if I take this and run, it should be printing out pretty quickly. Oops. I forgot to now put in that I wanted to print out, so I'll put in print equals 1. And you can see now it's displaying, we've done all these different percentages. And so you have some idea of how the program is running. If I change that 1 to a 2, it would no longer print that. And so, since the computer should always be doing something, I might as well just have it, running right now as we talk, and just see how bad is it. So it was about 8 seconds to do that run. And so it should be pretty linear in terms of how much longer it takes, because it's not a very long involved program that pulls it all together. So we've now done 10%, we've done 20%, but I'm not telling you what the success rate is to date, which is really frustrating. It's not that hard to just do that division. And so if the program fails, you at least have that. When you're running simple programs like this that take on the order of a couple of seconds to a minute, it's not a big deal. But as you start to do more difficult problems, then this is extremely important. You really want to save data to files so that if you have to do something, you don't have to keep doing it again and again and again. If it's something that you need, save it to a file, pull it in. Save your results. Always have 2 copies of any key program that you're using. God forbid there's a power outage or something goes wrong as you're saving the file and updating it, you could lose everything. And I know students who have lost everything like that. Have backups, have good names for your file. You know, untitled 1 star, not a great name. You should never run a program before saving it. So this was, you know, really bad on my count. So I should immediately save it right now. I'll deal with that after class. Any questions on this? I'll just take a quick snapshot of this. Just post this in the lecture. Now start the share. So let's just do one last thing very quickly. Okay. So let's say I want at least 2 queens and at least 3 kings. No, and at least 2 kings. What are the possibilities? Just tell me structurally what the hand can look like. Okay, so it could be queen, queen, king, king, other. Okay, what else could I have? I could have 3 queens, 2 kings. And that would be the same as, so I could calculate them, right? And so it's not that bad to calculate all of these. If I wanted to do the code, how should I code it? What would my deck look like? So I could have 1 to 52 and cards, you know, 1, 2, 3, 4 kings. Yes. Okay, that's a little, so you have the right idea of giving kings and queens different values, but 2 and 1 are very close. You can go through and then say, in that case, you know, to have 2 queens and 2 kings, that'd be 1, 2, 4, 6. But if I had 3 kings, that would also give me a sum of 6. 1 and 10. So I could do 10, 10, 10, 10, 1, 1, 1, 1, and then all zeros. And if I do it like that, I need a sum of 22, 23, or 32. Notice how much easier that is. If you're doing Sudokus, any of you have ever done a Sudoku? So my wife and my mother find it, I won't say, they would not do Sudokus the way I do, which is to write, of course, a computer program to solve it. And to me, the interesting part is actually coding the different steps you need to do. How many checks do you have to do in each row? To see if a row is correct, how many checks? Why 2 checks? No, but I'm saying for a row, how do you know if a row is correct? How many checks, how many things you have to look for? Well, you've got to be careful because, you know, maybe there's other ways to factor things. You need to check to see, do you have a 1, do you have a 2? If you just add them, you know, 1 through 9, you could have also 1, 1. So for Sudokus, do 1, 10, 100, 1000, and then add, and then unless it adds to 1, 1, 1, 1, 1, 1, 1, 1, you immediately know that you have a mistake. So you want to encode things in such a way that you have one and only one way to do it. All right, this is a good place to stop. I will send